Hello, I'm Kwang Che, and I'm honored to present our paper, Distilling a Pre-trained Language Model to a Multilingual ASR Model, which aims to distill the rich knowledge embedded inside a well-trained teacher-text model to the student's speech model. This work is done under the supervision of Hyungmin Park. The presentation is structured as follows. We first skim through the motivation of our paper to understand our method easier. Also, we briefly discuss which problem setting we chose in the motivation section. Even though our distillation method is extendable to many various problem settings, we concentrate on the multilingual automatic speech recognition task in this work. Then we go through each component of our method in detail and show our results and analysis. And finally, we summarize our work and discuss future works based on our paper. So our main motivation is based on two ideas. First idea is that there have been many advancements on the NLP side, partly because an abundant amount of data was generated from the web, and it is widely available to everyday researchers. However, speech data is obviously often more expensive to acquire, especially for the less popular languages. That's why we were especially interested in the multilingual ASR problem. Furthermore, there have been many advancements on the NLP side, especially for the transformer architecture. It is now empirically proven that large general language models based on transformers are filled with linguistic information. Hence, we are highly motivated to utilize the well-trained transformer-based language models to solve the multilingual ASR task, where we often encounter a limited dataset size, only a couple of hours available, especially for the less popular languages. So, as we will show it later, we concentrate on the case where we only have less than 100 hours of speech, with the lower bound of 1 hour. We focus on the specific family of methodologies, the knowledge distillation. The monumental Hinton paper first introduced the notion of knowledge distillation, where the main idea is to distill the knowledge embedded inside the teacher model A to the student model B. After that, there were many advancements on knowledge distillation, especially for the transformer architectures. To name a few, some try to distill knowledge by minimizing the distances between intermediate features or attention weights. However, we have to solve this essential problem. Can we distill from the language model to the speech model, despite the fundamental differences in modality? We believe we can. There are two main ingredients to tackle this. First is the knowledge distillation between transformers. Thankfully, all the modalities are merging towards transformers, and the current state-of-the-art ASR models are often based on transformers also. So we can borrow the ideas from the advancements in knowledge distillation within language models. However, text and speech are quite different, as text is highly compressed and tokenized compared to speech data. So, we employ various methods that can handle different dimensionalities, namely in terms of feature or temporal dimensions. We will go through the details later, but we use the shrink mechanism, interpolations, and projections to elevate the problem. Note that this differs from attaching a language model to enhance the speech model's prediction. We aim to improve the speech model's capabilities by distilling the inherent knowledge embedded inside the language model to the speech model, not further modify the output predictions using the language model. Two approaches are orthogonal. Hence, one can use both our method and attach the language models such as n-grams to further increase the ASR performance. So, let's dive into the details. There's quite a lot of information in this diagram, so we will walk through each components one by one. First, let's briefly review how ASR models are trained on the wave-to-vec model, which is a transformer-based state-of-the-art ASR model. We input the raw audio to the model to yield the speech feature HSM. The output feature map is two-dimensional. The width represents the temporal dimension, and the height represents the feature dimension. We put the common linear head to the feature per each time step to yield a stepwise prediction. Then we minimize the CTC loss with the ground truth text output to train the linear head and the speech encoder. Our work aims to distill the knowledge of the teacher text encoder to the student speech encoder. There are multiple ways to do so, but we concentrate on the output features of speech and text encoders. To distill the knowledge, we freeze the text encoder and train the speech encoder by minimizing the distances between two features, speech feature HSM and text feature HLM. This will guide the information embedded inside the text features to be distilled into the speech model. Both speech and text models are based on transformers, so both features are two-dimensional, temporal side and feature side. However, the dimensionalities between the two features are widely different. In this example, the speech feature has 10 time steps, and the text feature has 2 time steps. And the feature dimension is 5 and 3 for speech and text features, respectively. So our method concentrates on handling the different dimensionalities, which we will describe in the following slides. Recall that there were two dimensionalities, temporal and feature. So we first align the temporal side and then align the feature side. We apply two tricks to align the features. First is the shrink method for the speech features. The shrink method is nearly identical to understanding the CTC trained model's prediction outputs. We skip the empty tokens and average the consecutive tokens. In the above example, there are two A's and later three A's, so we average the speech features based on those two A's and three A's. And after reducing the temporal dimension of the speech features, we expand the text features to meet the speech features temporal dimension. We simply use the nearest neighbor to interpolate the two different dimensions. However, even after aligning the temporal dimension, we still have to align the feature dimension. We simply add a learnable projection layer to match the dimension of the speech feature to the text feature. This idea is also used in knowledge distillation between language models. However, in that case, one doesn't need to take care about the temporal dimension, as one can use the common tokenizer. However, due to the different modalities, we had to apply various methods to reduce the temporal discrepancy between different modalities, text and speech. Finally, after making the dimensions equal, we can at last minimize the distances between the speech and the text feature. We used the simple mean squared error loss in our experiments to minimize the distance between features. The final loss is the weighted sum between the two losses, ASR and KD. We trained the speech model by the CTC loss to solve the ASR problem, and we further aid the speech model by jointly using the KD, knowledge distillation loss, by minimizing the distance between the speech and the text features. Let's summarize our method. Distill language to speech, L2S, by looking at the full diagram. By passing the raw audio to the speech encoder, we result in a two-dimensional speech feature with temporal and feature dimensions. By applying a common linear layer to the features of each time step, we yield stepwise predictions for the ASR task. We use the CTC loss to train for the ASR task, and in the meantime, we pass the ground truth text to the text encoder to yield the text feature. Then we minimize the distance between speech and text features by the mean squared error loss. To mitigate the dimensional differences between the two features, we apply the shrink method and the nearest neighbor interpolation to match the temporal dimension. We further match the feature dimension by the learnable projection layer, and by minimizing the distances between two features, the knowledge embedded inside the text model is distilled into the speech model. To show the effectiveness of our method, we use the Common Voice dataset, which contains 60 different languages. Out of all the languages, we chose 20 languages by two criteria. The speech data should contain between 1 to 100 hours of speech data. We use the XLSR Wave2Vec2, which is the multilingual variant of the famous Wave2Vec model, as the student speech model. Also, the language has to be sufficiently covered by the text model, the InfoXLM model, trained with more than 1 gigabytes of text data per language. We use the InfoXLM for the teacher text model, which is the recent state-of-the-art cross-lingual text model. We first compare training from scratch and fine-tuning from the pre-trained weights of XLSR Wave2Vec2. We compare using CER as we concentrate on improving the speech model performance without the help of additional attached language model that modify the final predictions. We again confirm the effectiveness of the Wave2Vec2 XLSR model, which is the state-of-the-art for multilingual ASR. Finally, we compare the vanilla fine-tuning XLSR with our method Distill L2S. The best performance is written in bold. We can clearly observe that by using our method, we can further improve the state-of-the-art for all the languages. However, as some languages are improving much more better than others, we conduct further analysis on each language-wise performance. To analyze why some languages show limited improvement, we compared the two classes, languages with more than 10% or less than 1% relative CER improvement. We analyze in terms of the ground truth text length and the prediction density, which is the ratio of non-blank predictions of the speech model. We can see that both factors negatively impact performance. We suspect that both the text and speech features get lengthy. It is more likely for the temporal misalignment to occur, showing the limitation of the shrink method and the nearest neighbor interpolation. Further work on this issue needs to be done to improve the performance further. We end this presentation by going over the conclusions and future works. This work aims to utilize the well-trained cross-lingual text model, which is powered by the abundant amount of multilingual text data online, to enhance the performance of multilingual ASR, where it's much more expensive to obtain speech data, especially for the less popular languages. The experiments on the Common Voice datasets across 20 languages demonstrate that it is indeed possible to distill knowledge from the text model to the speech model to enhance performance. However, further work on the temporal misalignment issues needs to be done to improve the performance even further. Finally, but not the least, we open sourced our work to fuel the multilingual ASR research further. Thank you for listening. Feel free to ask questions or leave comments via this email or the issue tab in the open source GitHub repository.